Antimatter sounds like a prop from a science fiction film. A vial of glowing fuel, a warp drive humming in the dark, a weapon small enough to fit inside a briefcase. Most people picture it as opposite stuff, a dark mirror of the world where the rules run backward. That picture is wrong in nearly every way. Here is the number that should hold you still for a moment. For every 1 billion particles of antimatter the young universe made, it made 1,000,000,001 particles of ordinary matter. One extra particle in a billion. That is the whole margin. When the universe cooled and the two kinds met, they destroyed each other almost perfectly, and nearly all of it turned to light. What survived was that thin remainder, 1 part in a billion, and out of that remainder came every galaxy, every star, every planet, and you. You're built from the leftovers of a war that very nearly ended in a draw. Hold on to that, because the second number is just as strange. Take 1 gram of antimatter. Let it meet 1 gram of ordinary matter, about the weight of 2 small paper clips resting in your palm. The 2 grams do not burn or explode in the ordinary sense. They erase each other. The energy released is about 9 times 10 to the 13th joules. That is roughly 21.5 kilotons of TNT. It is more than the bomb that fell on Nagasaki. Drawn out of 2 grams you could close your hand around. So antimatter is not a fantasy metal and not a mystic force. It is ordinary physics turned by 1 small degree, and that 1 degree is enough to unmake whatever it touches. Before we go any deeper, 1 small thing. If quiet, factual space at this hour is what you came for, follow along and subscribe so the next one finds you in the dark. These are on Spotify as well. That is all I will ask. Now settle back and let us look at what antimatter actually is. Start plain. Every particle you are built from has a twin. The electron has 1, the proton has 1, the neutron has 1. Physicists call the twin an antiparticle, and the rule that binds them is beautifully simple. The antiparticle has the same mass as the particle, it has the same spin, it carries the opposite electric charge, and its other quantum properties are reversed as well. Same weight, same turning, opposite sign all the way down. Picture a coin struck from a single mould. One face is raised, the other pressed inward. Same metal, same width, same weight settling into your hand. They differ in 1 property only, and that 1 property decides what happens when they touch. The twin of the electron is called the positron. Same tiny mass, but a positive charge in place of a negative one. The twin of the proton is the antiproton. Same mass as a proton, negative where the proton is positive, with its magnetic behavior flipped as well. The neutron carries no overall charge, and yet it too has a twin, the antineutron, because a neutron is built from smaller charged pieces, and every one of those pieces reverses. Nothing is exempt from the pattern. Give physics any particle at all, and it can name you the mirror. Now put an antiproton at the centre, and let a single positron circle it. You have just built antihydrogen. It is the simplest atom of antimatter there is. It mirrors ordinary hydrogen, the simplest and most common atom in the whole universe, almost exactly. If you could hold a flask of antihydrogen gas without letting it touch anything, it would look like nothing at all. Clear, neutral, invisible. It would behave like ordinary hydrogen gas in every test you could run, right up to the instant it met the glass, and then it would be gone in a wash of light. Let the masses settle, because the figures are exact. A proton weighs about 1.67 times 10 to the minus 27th of a kilogram. The antiproton weighs precisely the same. Both are about 1,836 times heavier than a single electron or positron. This is why antiprotons were so much harder to find in the first place. A positron is light and cheap for nature to make. An antiproton needs almost 2,000 times the energy, which is why it stayed hidden from us far longer than its lighter cousin. And here is a quieter fact that will matter later. The photon, the particle of light itself, is its own antiparticle. Light has no separate mirror twin. It sits at the very center of the pattern, being both at once. This is why, when matter and antimatter meet and annihilate, the destruction shows up as light. Not ordinary light, but gamma rays, the most energetic radiation there is. Two particles that each weighed something become pure energy, racing outward. Mass goes in. Light comes out. Nothing solid is left behind but the flash. Think about what opposite charge truly means at this scale. An electron and a positron feel a pull toward one another because opposite charges attract. They drift together, they touch, and both of them cease to be particles at all. Their combined mass converts into two flashes of gamma light, flying apart in exactly opposite directions. This is not rare, and it is not only cosmic. It is happening inside hospitals at this very hour, quiet and controlled and useful, in a way we will return to before the night is through. Now let us clear away the largest myth of all. Antimatter is not anti-gravity. It does not fall up. It is not a substance that floats or repels the ground or breaks the ordinary laws of motion. For decades this was an open question, because no one had ever managed to drop a piece of antimatter cleanly enough to watch. In 2023, an experiment at CERN called Alpha G finally did it. Physicists trapped antihydrogen atoms in a magnetic bottle, then released them and watched where they went. The atoms fell downward, the same direction your own body falls. They measured the acceleration at about 0.75 times normal gravity, well within the roughly 20% uncertainty of that first attempt. Antimatter has weight, and gravity pulls it down like anything else, so the mirror is faithful in almost every direction. Same mass, same spin, same fall toward the Earth. The only clean difference is the flipped sign of charge, and charge on its own tells you nothing about how much of the stuff should exist. Now, take the pattern to its unsettling end. Suppose you could build an antimatter version of yourself, not a metaphor, but an exact copy. Atom for antimatter atom. Every antiproton set in place of a proton, every positron in place of an electron, every bond, every fold, every structure the same. That double would wear your face and carry your weight. It would think, if it could think, the very thoughts you're thinking now. In every experiment ever devised, it would behave exactly as you do. You would not be able to tell the two of you apart by any measurement. There is only one difference, and it is complete. The moment your antimatter twin brushed against anything made of ordinary matter, a wall, a hand, a single breath of air, the two of you would stop existing. Not fall, not burn, not wound, vanish. The full mass of both bodies would pour out as a flash of gamma light brighter than a nuclear weapon. That is the strangeness sitting at the heart of all this. A perfect copy that can never share a room with the original, because the smallest contact means mutual erasure, and the record of it is written only in light. And yet, when physicists set the twin beside the original and measure, they find no flaw in the mirror at all. At CERN there is an experiment called BASE, built to do nothing but compare the antiproton to the proton with almost unbelievable care. It has measured their charge to mass ratio and found the two identical to within 16 parts in a trillion. 16 parts in a trillion. Take a number with 12 zeros and allow yourself to be wrong by only 16 at the very end of it. That is how closely the antiproton matches the proton. The same team pinned down the antiproton's magnetic moment to about 1.5 parts in a billion, sharpening an older measurement by more than 3,000 times. Every reading says the same quiet thing. They are the same. That is the wall the whole mystery runs straight into. Antimatter is not weaker. It is not backward. It is not some lesser shadow of the real thing, measured against ordinary matter to the outermost limits of human instruments. It is a perfect equal. The masses match. The spins match. The strength of the forces holding it together matches. It even falls the same way through the same gravity. The only difference we can find is a flipped sign, and a flipped sign changes nothing about how much of it the universe was obliged to make. So the equations stay calm and confident, and they say something almost unbearable. They say the Big Bang should have made matter and antimatter in exactly equal amounts. Equal parts, born together in the same fire, cancelling one another completely, leaving behind a universe of nothing but light and no one anywhere to notice the emptiness. That is the honest outcome the physics predicts, a cosmos that flares once and goes dark. Instead, here you are, in a body, in a world, beneath a sky full of stars that, by every rule we can write down, have no business existing. Somewhere in the first fraction of a second, that perfect balance failed by the smallest margin nature allows. One extra particle of matter for every billion matched pairs that annihilated into light. Before anyone ever saw a scrap of it, antimatter was written down as an accident in an equation. The year was 1928. A quiet English physicist named Paul Dirac was trying to do something modest. He wanted a single formula that described the electron correctly, one that honoured both the rules of quantum mechanics and the rules of Einstein's relativity at once. Nobody had managed to fit those two worlds together for a moving particle. Dirac sat with the mathematics until it clicked, and out came an equation of rare and unsettling beauty. Then the equation did something he had not asked it to do. It handed him two answers instead of one. One solution described the ordinary electron, the small negative speck that carries electricity through every wire in your home. The other solution described a particle with exactly the same mass, exactly the same behaviour, and the opposite charge. Positive where the electron was negative. A mirror twin that no one had ever seen, that no experiment had ever hinted at, sitting there the math as calmly as the electron itself. Dirac did not trust it. This is the part worth sitting with. The man who wrote the equation was the first person to doubt what it was telling him. A stray, positive solution looked like a mistake. The kind of thing that falls out of an equation and means nothing physical. For a while he tried to explain it away. He wondered if the second answer might somehow be the proton, the heavy, positive particle already known to exist. But the numbers refused. The mirror particle had to weigh the same as the electron, and the proton weighs far more. The equation was insisting on a brand new object. It was describing a piece of reality that had never been observed, and it would not take the description back. That is the shape this whole story keeps returning to. The mathematics saw the thing first. The mirror world existed on paper years before it existed in any laboratory, and the equation was more certain of it than the man who discovered the equation. Proof arrived in 1932, and it arrived from the sky. Across the country, at Caltech in California, a young physicist named Carl Anderson was studying cosmic rays. These are particles that pour down onto the Earth from deep space, striking the top of the atmosphere at tremendous speed. To catch them, Anderson used a cloud chamber. Picture a sealed glass box filled with a cold, saturated vapor. When a charged particle races through that vapor, it leaves a thin trail of condensation behind it, the way a jet leaves a white line across the sky. A hairline thread of mist, marking the path of something far too small to ever see. Anderson wrapped his chamber in a strong magnet. A magnetic field bends the path of a charged particle, and the direction it bends tells you the sign of the charge. Negative particles curve one way, positive particles curve the other. So he sat and photographed thousands of these vapor threads, reading the curl of each one like handwriting. Then one photograph stopped him. A track curved the wrong way. The trail had the delicacy of an electron, the same thinness, the same tightness of turn that meant the same tiny mass. But it bent in the direction reserved for positive charge, an electron's mass with a proton sign of charge. It was precisely the impossible particle Dirac's equation had refused to give up 4 years earlier. Anderson gave it a plain name. He called it the positron, the positive electron. Think about what that photograph actually was. It was the first physical footprint any human being had ever seen of antimatter. Not a theory, not a symbol on a chalkboard, but a real curling thread of mist left by a real piece of anti-reality passing through a box in California. A splinter of the mirror world had fallen out of space, drawn its signature in vapor, and vanished. Anderson had caught its shadow on film. For that single photograph, and the careful work behind it, he would receive the Nobel Prize in Physics. So by 1932, the detective story had its first confession. The math had predicted a mirror twin for the electron, and nature had produced one on cue. It was natural to assume the rest would follow quickly. If the electron had an antiparticle, then surely the proton had one too. An antiproton, a heavy negative twin of the positive workhorse that sits inside every atomic nucleus. Everyone expected it. Almost no one guessed how long it would hide. The antiproton would not be caught for another 23 years. The reason is a matter of sheer weight. A proton is a heavyweight compared to an electron. It carries roughly 1,836 times the mass. And to manufacture a particle, you have to pour in energy equal to its mass, because mass and energy are two faces of the same coin. Making an antiproton therefore demanded far more energy than making a positron. The positron came free, delivered by cosmic rays out of the sky. The antiproton could not simply be waited for, it had to be built, and to build it, physicists had to build a machine large enough and violent enough to bottle up that much energy in one place. That machine was constructed at the University of California at Berkeley. They called it the Bevatron, a giant ring of a particle accelerator designed to whip protons up to enormous energies and slam them into a target. The idea was straightforward and brutal. hit ordinary matter hard enough, concentrate enough energy in a small enough space, and new particle and antiparticle pairs should burst out of the collision. Somewhere in that spray of debris, an antiproton should be waiting if it existed at all. In 1955, it appeared. Two physicists, Emilio Segre and Owen Chamberlain, led the hunt. The problem was that the collisions threw off a storm of ordinary particles for every rare antiproton, and they needed to be certain. So they built a careful filter. They measured the mass of each candidate and the sign of its charge and its speed, and they demanded that everything match a proton exactly, except with the charge flipped negative. Only a genuine antiproton could pass every test at once. Enough of them did. The heavy negative twin was real. Segre and Chamberlain would share their own Nobel Prize for it, awarded in 1959. Now the pattern in the detective story stands out clearly. Dirac wrote the equation, and the equation quietly insisted the mirror particle had to exist. Then Anderson found the positron in a cloud chamber. Then, after 2 decades of building bigger machines to reach higher energies, Segre and Chamberlain dragged the antiproton into the light. Every time the same order of events. The mathematics went first. It laid down the prediction, sometimes years or decades ahead, and the physical proof came trailing behind, confirming what the numbers had been saying all along. That order is worth holding on to because it is not how we usually imagine science working. We picture someone stumbling onto a strange fact and then scrambling to explain it. Antimatter ran the other way. The strange fact was demanded by the theory before anyone had laid eyes on it. Reality, it turned out, had been keeping a full set of mirror pieces all along, one for every particle we knew, each identical in mass, each opposite in charge. Give the electron a partner, give the proton a partner, and you could begin to picture an entire mirror inventory of the universe, a complete anti-version of ordinary stuff, waiting in the equations to be found one careful experiment at a time. Which raises the question that turns this from a tidy detective story into a genuine mystery. The math said matter and antimatter should stand as perfect equals. Every twin balanced against its partner, same weight, opposite sign, made in matching pairs whenever enough energy gathered in one place, and the experiments agreed. Positron balanced electron, antiproton balanced proton. Nature was building both sides of the ledger with the same steady hand. So the mirror world was real, and it was symmetric, and it was everything the equations had promised. Then you look up at the sky, and at the ground, and at your own hands, and you find that the balance broke. The universe around you is made of matter almost entirely, with the antimatter twins nowhere to be seen in bulk. Somewhere between the perfect equation and the world you actually live in, a fraction of the balance tipped, and it tipped in favor of the stuff you are made from. And that single missing particle in a billion is the only reason you are here tonight to wonder where the rest of it went. And that single missing particle in a billion is the only reason you are here tonight to wonder where the rest of it went. So follow that thread back with me. Follow it all the way to the beginning, to the first thin slice of a second after everything began. Because the strangest part of your existence is not that you are made of matter. The strangest part is that by our best equations you should not be made of anything at all. Here is what those equations say. In the first instant of the Big Bang, the universe was pure energy. And pure energy makes particles in pairs. It always makes them in pairs. When enough energy condenses into matter, it does not produce a single lonely particle. It produces one particle and its exact antiparticle together, born in the same breath, carrying opposite charges that cancel to zero. That is the rule, and it does not bend. The books balance every time, which means the early universe should have made matter and antimatter in exactly equal amounts. Not roughly equal, perfectly equal. The energy that forged a quark had no reason to prefer it over an antiquark. It could not tell them apart. To the raw furnace of creation they were the same coin, minted in identical numbers, poured into space side by side. And yet you look around tonight and you see only one side of that coin. Every star you have ever seen is matter. Every planet, every grain of dust, every atom in your own hand is matter. The antimatter is simply gone. Before we walk into that furnace, take a breath with me. If you are finding some quiet in this, a like or a subscribe helps these long nights reach other people who cannot sleep. We are also on Spotify if you drift better with just the voice. That is all. Now, back to the fire. Picture the universe when it was younger than a heartbeat. There were no stars. There were no atoms. There were not even protons yet, because it was far too hot for a proton to hold itself together. The temperature was near 10 to the 12th Kelvin. Say that number slowly. 1 trillion degrees on the Kelvin scale, which is roughly 1.8 trillion degrees Fahrenheit. At that heat, matter cannot be solid, or liquid, or gas. It cannot be anything you have a word for. Instead, all of space was filled with a kind of fog. Physicists call it a quark-gluon plasma. It was a seething soup of the smallest pieces of reality. Quarks and the gluons that would one day bind them, all of it loose and free and colliding at nearly the speed of light. Nothing could settle. Nothing could cool into a shape. Every quark in that fog had an antiquark drifting somewhere nearby, its perfect opposite, and the two of them were on a collision course that had only one possible ending. Because this is the thing about a particle and its antiparticle. When they touch, they do not bounce. They do not merge into something larger. They annihilate. Both of them cease to exist as matter in the same instant, and every ounce of their mass converts into pure light, into gamma radiation, flooding outward at the fastest speed there is. Matter meets antimatter, and both are gone, and the universe grows a little brighter and a little emptier. So in that first fraction of a second, this was happening everywhere, all at once, across all of space. Quarks and antiquarks finding each other in the fog and vanishing into flashes. The universe was annihilating itself. It was a bonfire eating its own fuel, and the fuel was almost everything that existed. This annihilation epoch did not last long by a clock, but it was long by the standards of the early universe. It ran from the first sliver of a second out to somewhere around 100 seconds. In that window the heavy particles went first. By about 25 microseconds after the beginning, the great annihilation of the quarks and antiquarks was already mostly finished. The heaviest players in the drama had already met their mirror twins and burned away into radiation. 25 microseconds. That is far less time than it takes you to blink. In that impossibly narrow slice, the bulk of the matter and antimatter that would ever exist had already found each other and cancelled out. What remained afterward were only the lighter carriers of antimatter, the electrons and their opposites, the positrons, the ghostly neutrinos and their antineutrinos. These lingered a little longer in the cooling universe, still pairing off, still annihilating, still thinning the fog toward emptiness. And here is where you have to hold the numbers in your mind, because the numbers are the whole story. When the great cancellation was done, when nearly every particle had found its antiparticle and disappeared into light, more than 99.9999999% of everything was gone. Over 9 nines of all the matter and antimatter that the Big Bang ever made had erased itself. What was left was a faint residue, a remainder so small it barely deserves the name. That remainder is you. That remainder is the ground beneath you and the air in the room and the light of every galaxy. Everything you will ever touch or see is the ash left in the grate after a fire that consumed almost the entire fuel supply of creation. You are not the flame. You are the little that would not burn. Now why did anything survive at all? Why was there a remainder instead of nothing? This is the heart of it. If matter and antimatter had truly been made in perfectly equal amounts, then every single particle would have found a partner. Every quark would have met an antiquark. Every electron would have met a positron. The books would have balanced to 0 exactly with nothing left over, and the universe would have ended almost as soon as it began. Sit with that for a moment. A perfectly even split, which is exactly what our best equations predict, would have written the shortest story imaginable. Total mutual annihilation into light, finished inside the first second. No stars would ever form, no galaxies would gather, no planets, no oceans, no first living cell, no last human thought, just an endless, expanding bath of gamma radiation, cooling forever, with no one anywhere to notice how empty it was. A universe that made itself and unmade itself in a single breath. That is the universe the equations describe. It is a universe that should have been stillborn. And the only reason it was not, the only reason there is a cosmos with things in it, is that the split was not perfectly even. It was off like the tiniest sliver you can imagine. The number that physicists at CERN and cosmologists everywhere keep coming back to is roughly this. For every 1 billion antimatter particles, there were about 1 billion and 1 matter particles. Read that ratio out loud because it is almost absurd. 1 billion and 1 against 1 billion. A single extra grain of matter for every billion pairs. That is the entire margin. That razor's edge is why there is a universe of galaxies instead of an ocean of cold light. Think about what that one extra particle in a billion actually did. When the annihilation swept through, each of those billion antimatter particles found a matter partner and burned away with it. 2 by 2 they cancelled, and their mass poured out as radiation. But that one lonely extra matter particle in every billion had no partner left to meet. Its opposite had already been used up, so it survived. It could not annihilate because there was nothing left to annihilate with. It stayed behind. Multiply that survival across the whole young universe, and the leftover ones add up. Not to much compared to what was lost. The photons that came out of all that annihilation still outnumber the surviving matter particles by about 1 billion to 1, and those photons are still around you tonight, cooled over billions of years into the faint microwave glow that fills the sky. But the leftover matter, that thin 1 in a billion residue, was enough to make hydrogen, enough to make the first stars, enough to forge carbon and oxygen and iron in stellar furnaces, and to scatter them, and to gather them again into worlds, enough eventually to make you, lying here, warm and breathing and improbable. You are the survivor of a slaughter you never saw, not a survivor by strength, a survivor by accounting error, a rounding difference in the ledger of creation that should have summed to nothing. So the great question hangs over all of it. Where did that error come from? What tipped the scales by 1 part in a billion? Because remember, the energy that made the pairs was supposed to be blind. It was supposed to make matter and antimatter in numbers so exactly equal that nothing could survive. If the rule held perfectly, the ratio would be 1 to 1, and you would not be here to hear about it. Something broke the rule. Something, somewhere in the first instance, quietly favoured matter over antimatter, just barely, just enough. And this is not a small crack to explain away. Physicists have looked hard for the missing antimatter, in case it did not really vanish, in case it is simply hiding. They have searched the solar neighbourhood, the gas between the stars, other galaxies, whole clusters of galaxies. Everywhere they look, everything they can measure is ordinary matter. If a galaxy of antimatter existed out there, its edge would grind against the ordinary gas that fills the space between galaxies, and that contact would blaze with a steady, unmistakable gamma-ray glow. That glow has never been seen, not anywhere, at any scale. The universe is silent in exactly the way it would be if the antimatter is genuinely gone, not hidden. Which forces a hard conclusion. The antimatter did not run away and conceal itself. It was destroyed, along with almost all the matter in that early fire, and the matter that remained is here only because of that faint imbalance built into the beginning. So the imbalance is real, and it is the deepest kind of clue. It tells you that somewhere in some process nature does not treat matter and antimatter as perfect equals. The mirror is not flawless, there is a smudge on the glass. That was the realization that reshaped the whole question. For a long time the assumption was symmetry. Matter and antimatter were understood as exact reflections, identical in every way that mattered except the sign of their charge. Same mass, same spin, same rules. If that were entirely true, the universe would be empty, so it cannot be entirely true. Your existence is the proof that somewhere the reflection fails. In 1967, the Soviet physicist Andrei Sakharov wrote down what any answer would have to satisfy. He laid out 3 conditions. First, some process must be able to create more matter particles than antimatter particles, breaking the strict bookkeeping that keeps them equal. Second, physics must treat matter and antimatter slightly differently, a genuine asymmetry in the laws themselves. Third, all of this must happen while the young universe was out of balance, changing too fast to settle into a steady, symmetric calm. Meet those 3 conditions, and a lopsided universe becomes possible. Miss any one of them, and you are back to empty light. Sakharov did not tell us where the smudge was. He only told us it had to exist, and what shape it had to have. He turned a mystery into a search with rules. And the second of his conditions is the one that points like an arrow. Physics must treat matter and antimatter differently, not by much, by enough. Somewhere in the behaviour of particles there must be a place where a thing and its mirror twin do not do quite the same thing. That is a strange claim to make about a mirror. You expect a reflection to move exactly as you move. Raise your right hand, and the reflection raises what looks like a left hand, but the motion is faithful, instant, complete. What Sakharov's second condition demands is a reflection that lags, or leans, or chooses. A mirror world that is almost identical to ours, but not quite, in a way so subtle it took the sharpest instruments ever built to catch even a whisper of it. And so the whole grand mystery of why you exist, why the universe kept anything at all, came down to something almost delicate. Not the fire, not the trillion degrees, not the vanished billions. Those were the consequences. The cause had to be smaller and quieter, a tiny preference, hidden in the fine print of physical law that let matter outlast its twin by 1 part in a billion. Finding that preference became one of the great hunts in all of science. It meant looking at particles decaying one by one billions of times over, watching for the moment when a particle and its antiparticle refused to behave as perfect mirrors. So the search narrowed to a single question, the exact place where nature quietly tells matter and antimatter apart. So the search narrowed to a single question, the exact place where nature quietly tells matter and antimatter apart. Physicists gave that place a name. They call it CP violation. The letters stand for 2 ideas held together. C is charge, the property that flips a particle into its antiparticle. P is parity, which mirrors the geometry of space, left for right. The way a reflection reverses a glove. Do both at once, flip every charge and mirror every direction, and the equations promised that matter and antimatter should behave identically. For a long time that promise looked airtight. Then in 1964 it broke. The break came from a strange short-lived particle called the neutral kaon. Kaons are unstable. They form in high-energy collisions and then fall apart within fractions of a second. Physicists studying how they decayed found something that should not have been there. A tiny fraction of these particles decayed in a way the mirror symmetry forbade. The imbalance was small, roughly 2 parts in 1,000, but it was real. Nature was not perfectly even-handed. Matter and antimatter were not exact reflections after all. That discovery earned a Nobel Prize, and it changed the question everyone was asking. The universe was not symmetric. It only looked that way. Before we go further, one small thing. If these quiet cracks in the universe are the kind of idea you want more of, a like or a subscribe helps this channel keep making them, and every episode is on Spotify too. That is all. Now, settle back and let the strangeness take over. Think about what that 1964 result really meant. For every rule that says matter and antimatter are twins, here was one place the twins could be told apart. That felt like a doorway. If the early universe could tell the difference even a little, maybe that little difference was enough to leave some matter behind. Maybe the survival of everything traced back to this hairline imperfection in the laws themselves. It was a beautiful thought. It has also turned out to be one of the most frustrating leads in all of physics. 3 years after the kaon result in 1967, a Soviet physicist named Andrei Sakharov wrote down what it would actually take. He listed 3 conditions. Any universe that starts balanced and ends up lopsided in favor of matter must satisfy all 3. Miss even one, and you stay perfectly symmetric, which means you annihilate into light and end with nothing. The first condition is the boldest. Somewhere, some process must be able to create more matter particles than antimatter particles. Physicists call this baryon number violation. In everyday physics, matter is conserved. You cannot simply make an extra proton from nothing. But to explain us, the early universe had to break that bookkeeping at least once, tipping the count toward matter. The second condition is the one the kaons pointed to. Physics must treat matter and antimatter slightly differently. That means both C violation and CP violation. Without it, any process that made extra matter would be matched exactly by a mirror process making extra antimatter, and the two would cancel. You need a genuine bias, a thumb resting gently on one side of the scale. The third condition is about timing. All of this has to happen while the universe is out of balance, not sitting in a calm, steady state. Physicists call it a departure from thermal equilibrium. In equilibrium, every reaction runs both forward and backward at the same rate, and any advantage you build gets erased just as fast. You need a moment of change, a universe cooling and falling out of step with itself, so that the imbalance can freeze in before it washes away. Here is the quietly devastating part. The standard model of particle physics, our best and most tested description of reality, technically allows all three of Sakharov's conditions. On paper, the machinery is there. It can violate baryon number under extreme conditions. It contains CP violation, the very thing the kaons revealed. And the early universe certainly passed through moments of rapid change. So in principle, the recipe exists inside known physics, but principle is not enough. When you measure how much CP violation the standard model actually contains, the number is far too small, not a little short, not off by a factor of 10, off by many orders of magnitude. The known bias in the laws could account for only a tiny sliver of the matter we see. If the standard model were the whole story, the surviving matter should have been vanishingly smaller than it is, so small that galaxies could never have formed. Known physics allows a lopsided universe, it just cannot make one nearly lopsided enough to hold you. So the hunt continued. If the crack found in kaons was too small, maybe there were other cracks, wider ones, hidden in particles no one had checked yet. For 60 years the search stayed mostly in one family of particles. Kaons are mesons, made of one quark and one antiquark, a matched pair bound together. CP violation was found again in other mesons too, in heavier cousins built from heavier quarks. Each time the effect was real. Each time it was still too small. And through all those decades, one whole class of matter stayed silent. That class is the baryons. Baryons are the particles you're actually made of. A proton is a baryon. A neutron is a baryon. Together they build every atomic nucleus, which means they build nearly all the ordinary mass in the universe. If any particles were going to explain why matter survived, you would want it to be these, the ones that became the actual stuff of stars and planets and bone. Yet for more than half a century, no one had ever caught a baryon breaking the mirror symmetry. The particles that made the world kept their secret. That silence ended in 2025. On March 21st of that year, and published in the journal Nature on July 16th, the LHCb collaboration at CERN announced the first observation of CP violation in the decay of baryons. They had been watching a heavy short-lived particle called the lambda B0 baryon and its antimatter twin. In a perfectly symmetric universe, the two would fall apart at exactly the same rate. They do not. Sorted through billions of recorded collisions, the particle and its antiparticle decayed at measurably different rates. The mirror was cracked here too, in the family that builds you. The result carried a strength physicists call 5.2 sigma. That is their threshold for calling something a discovery rather than a coincidence. In plainer terms, the odds that this was a random fluke sit at about 1 in 10 million. This was not a hint or a whisper. It was a confirmed fact about the deep structure of matter. For the first time, the particles that make up ordinary reality had been caught, red-handed, treating matter and antimatter differently. You might expect that to be the moment everything clicked into place. It was not. And this is where the whole long story turns quietly heartbreaking, because the LHCb baryons, like the kaons before them, and every meson in between, break the symmetry by an amount that is still far too small. Physicists have now caught nature bending its own rules in 3 separate families of particles, kaons in 1964, other mesons in the years since, and finally the baryons themselves in 2025. Every single time the bias is real, and every single time it falls orders of magnitude short of explaining why anything exists at all. Sit with that for a moment. You have a mystery that demands a certain amount of imbalance in the laws of physics. You go looking for that imbalance. You find it again and again, in place after place. And each discovery, thrilling as it is, only confirms that the imbalance is there, and confirms that it is nowhere near enough. It is like tracking a thief through a house, finding fingerprints in every room, and slowly realizing that even all the fingerprints together cannot account for everything that went missing. The 2025 baryon result is a genuine piece of the puzzle. It is simply not the whole answer. Most physicists now agree the whole answer must lie somewhere beyond the standard model. In physics we have not yet found. So where else could the missing imbalance hide? One of the most promising ideas turns the whole problem sideways. Instead of asking why there is more matter than antimatter among the heavy particles, it asks about the light, ghostly ones. This idea is called leptogenesis. Leptons are the family that includes the electron and, most importantly here, the neutrino. Neutrinos are almost nothing. They have a whisper of mass, no electric charge, and they pass through matter as if it were empty space. Trillions of them are streaming through your body right now, and nearly all of them will pass and clean through the entire Earth without touching a thing. Leptogenesis proposes that the original imbalance did not start with matter as we know it. It started with these ghosts. In the extremely early universe, an asymmetry could have appeared among the leptons first, favouring neutrinos over antineutrinos. Then, through processes the standard model already allows, that leptonic imbalance could have been converted into the baryon imbalance we see today. The matter you're made of would be a kind of inheritance, handed down from a head start that began with the lightest particles in existence. It is an elegant idea. It is also so far unconfirmed. To make leptogenesis work, neutrinos would need to show their own version of CP violation, behaving differently from antineutrinos. Experiments are hunting for exactly that. In Japan, a project called T2K has found suggestive hints that neutrinos and antineutrinos change their identities at slightly different rates. Hints, not proof. In the United States, an even larger experiment is being built to settle the question, firing a beam of neutrinos about 800 miles straight through solid rock, from Illinois to a detector buried nearly a mile underground in an old gold mine in South Dakota. It is designed in part to measure whether neutrinos violate the mirror symmetry strongly enough to make leptogenesis real. Its full results are still years away. The answer that could explain your existence may already be forming inside that beam, and we simply do not have it yet. This is the strange place the hunt has arrived. We have proof that the laws of physics are not perfectly even-handed. We have found the crack in the symmetry in kaons, in mesons, and now, at last, in the baryons that build the visible world. We have a clear list, written in 1967, of the conditions any answer must meet. We have a serious alternative idea waiting on experiments still underway. What we do not have is a mechanism large enough to explain the one plain fact that started all of it. The universe kept some matter. It kept far too much for the biases we can measure to explain. Something tipped the scale harder than anything we have caught in the act. And notice what all of this has been so far. It has been reading, watching particles decay and comparing the tallies, counting lambda B zeros against their antimatter twins in a detector, firing neutrinos through the crust of the Earth and measuring what arrives. Every one of these triumphs is an act of observation, of catching antimatter in the moment it falls apart and noticing the faint lopsidedness in how it goes. That is delicate, brilliant work, but it is still, in the end, watching from a distance as antimatter destroys itself. It never asks you to hold the stuff in place, to make an antihydrogen atom and keep it, to trap antimatter and study it at rest rather than in the flash of its own annihilation, is a task of a completely different scale. So consider the machines built to catch the crack itself. They have names and locations and numbers attached to them. The first sits underground on the border of France and Switzerland. It is called LHCb, one of the great detectors on the Large Hadron Collider at CERN. Its job is narrow and strange. It watches particles born from proton collisions, then reads how they fall apart. Billions of collisions pour through it. Most mean nothing. The detector is looking for a faint lopsidedness in the wreckage. In 2025, that patience paid off. The LHCb team studied a heavy particle called the lambda B0 baryon and its antimatter twin. A baryon is the ordinary kind of matter, the family that includes the proton and the neutron in your own body. The team measured how often each version decayed down a particular path. The two rates should have matched. They did not. The particle and the antiparticle came apart at measurably different rates. The strength of that result was 5.2 sigma. In plain terms, the odds of it being a random fluke are about 1 in 10 million. It was published in the journal Nature on the 16th of July 2025. For more than 60 years, physicists had seen this mirror cheating only in lighter, more exotic particles. Now, for the first time, they had caught it in a baryon, in the same class of matter that everything solid is made from. A single instrument, reading collision after collision, had found the asymmetry hiding inside ordinary stuff. It was a landmark. It was also not enough. The imbalance it revealed is still far too small to explain why the universe kept any matter at all. So the search widened into a stranger kind of particle entirely. That search runs partly through Japan, in an experiment called T2K. Here the hunters are not baryons but neutrinos, the faintest particles known, the ones that slip through solid rock as if it were open air. Neutrinos come in types, and they change from one type to another as they travel, a shifting motion physicists call oscillation. T2K sends a beam of them one way, then sends a beam of their antimatter versions, and compares. The question is simple to say. Do neutrinos and antineutrinos change at exactly the same rate? The early answer is a quiet maybe. T2K has found hints that they do not oscillate quite the same way. The result is not yet certain, but it is sharp enough to matter. The experiment has ruled out roughly 46% of the possible values for the neutrino's mirror-breaking parameter at 3 sigma confidence. That is a large slice of the map crossed off. It opens what physicists think of as a second front in the war on symmetry, a leptonic front, running through the lightest particles rather than the heavy ones. If the asymmetry began anywhere, it might have begun here, among the neutrinos, in the first flicker of the early universe. To press that idea harder, a bigger machine is being built across the middle of the United States. It is called DUNE, the Deep Underground Neutrino Experiment, and its scale is hard to hold in your mind. At Fermilab in Illinois, physicists will fire a beam of neutrinos into the ground. The beam will not follow a tunnel. It will simply travel straight through the solid rock of the continent because neutrinos barely notice matter at all. It will keep going for 300 kilometers, about 800 miles. At the far end in South Dakota, the beam arrives at a detector buried nearly a mile underground. The detector sits inside a former gold mine, in a place now called the Sanford Underground Research Facility. Miners once dug there for metal. Now the same deep rock shields a set of enormous tanks from the noise of the surface, so that a few of those invisible particles can be caught as they pass. The mountain of rock above becomes a filter, screening out everything except the faint signal the experiment wants. Dune was built with one great question near its heart. Is the mirror breaking among neutrinos large enough to matter? If neutrinos and antineutrinos differ by enough, that difference could, in theory, have seeded the whole imbalance through a process called leptogenesis. An asymmetry among the light particles could have tipped over, in the young universe, into the surplus of matter that became galaxies. Dune is meant to measure that difference cleanly, over years of the beam crossing 800 miles of rock again and again. Notice the timing here. Dune is still coming online, its full results are years away. T2K offers hints, not verdicts. So this is not a solved story you're hearing, it is a live one. The machines are running now, or being finished now, and the answer they are chasing has not yet arrived. The mystery is not closed, it is being pried at slowly by some of the largest instruments humans have ever built. And then there is the smallest and oddest hunt of all. It happened in November of 2025, and it did not fire a beam through a continent, it drove a truck. At CERN, an experiment called Base Step set out to do something no one had done before. They took a cloud of antiprotons, real antimatter trapped in a portable magnetic bottle, and they moved it. Not through a beamline, across the ground. The trap was loaded onto a vehicle and driven across the CERN site, carrying the antiprotons from one place to another, and the antiprotons survived the trip. None of them touched the walls, none of them annihilated. The cloud arrived intact. That may sound modest next to an 800-mile beam. It is not. Antimatter cannot touch anything. The instant an antiproton meets ordinary matter, both vanish in a flash of energy. So the cloud rode inside an invisible magnetic cage, held in the dead center of the trap, touching nothing at all, while the truck rolled over open ground beneath it. Picture a small caravan crossing the campus, carrying what looks like a crate of empty equipment. Inside, held apart from the whole material world, sits one of the rarest substances on Earth. A caged flame, driven across a parking lot, kept alive by fields alone. The point of the trip is patience again. The great collider halls are loud with electromagnetic noise, and that noise blurs the most delicate measurements. If you could carry a cloud of antiprotons away to a quieter laboratory, you could measure them more precisely and compare them against ordinary protons with even finer care. Base step was the first step toward that. It proved antimatter can be moved between labs without being lost. A cloud of it went for a drive and came back still there. Put these machines beside one another and a shape appears, a detector in a tunnel reading billions of baryon decays, a neutrino beam in Japan sorting matter from antimatter by the way it flickers, an 800-mile shot of ghost particles aimed at a mine in South Dakota, a truck carrying trapped antiprotons across a campus in a magnetic cage. Every one of them is built around the same faint suspicion. Somewhere the mirror does not hold. Somewhere nature treats matter and antimatter differently by a hair, and that hair is the reason there is anything to build instruments out of at all. None of them has closed the case. The baryon result is real and too small. The neutrino hints are suggestive and not yet sure. Dune has not yet spoken. The truck simply proved the cloud can travel. The asymmetry that let you exist is still tonight an open question, and these are the machines standing at its edge, listening. Reading the asymmetry in a decay is hard enough, but actually catching antimatter and holding it still is a problem of an entirely different kind. Reading the asymmetry in a decay is hard enough, but actually catching antimatter and holding it still is a problem of an entirely different kind. Reading the asymmetry in a decay is hard enough, but actually catching antimatter and holding it still is a problem of an entirely different kind. You cannot pour it into a jar. You cannot rest it on a table. The moment a single antiproton touches the wall of any ordinary container, it and a matching scrap of that wall vanish together into a flash of gamma light. So the whole trick of studying antimatter is the trick of never letting it touch anything at all. And before you can hold it, you have to make it, one impossibly small piece at a time. At CERN, near Geneva, there is a building people call the Antimatter Factory. The name sounds grand. The output is almost nothing. To make antiprotons, engineers take a beam of ordinary protons and slam it into a block of metal at nearly the speed of light. Out of that violent collision, among a spray of debris, a few antiprotons are born. They come screaming out fast, far too fast to catch. So the factory feeds them into a series of decelerator rings, machines whose entire job is to slow antimatter down. Ring by ring, the antiprotons are cooled and calmed until they are gentle enough to trap. Before we go further, if this quiet walk through the strangest material on Earth is holding you, a like or a subscribe helps this channel more than you would guess. We are on Spotify too for nights when you would rather only listen. That is the only time I will ask. Here is the scale of the effort. That whole factory, running at full tilt, delivers roughly 400 million antiprotons an hour. 400 million sounds enormous, until you remember that a single grain of sand holds vastly more atoms than that. And of those 400 million, the experiments managed to capture only about 10%. The other 90% are lost, drifting into a wall, annihilating in silence before anyone can study them. So the real harvest is a few tens of millions of antiprotons an hour, plucked from the wreckage and kept apart from every ordinary thing around them. Now comes the harder part. An antiproton carries electric charge, and a charged particle can be steered and pinned by magnetic and electric fields. That gives physicists a handle. They hold clouds of antiprotons inside what is called a penning trap, a cage made not of metal but of fields, a magnetic bottle with no glass and no walls. The antimatter floats in the dead center, touching nothing, suspended in empty space by invisible force. It is, in a real sense, the loneliest material in the universe, held forever at arm's length from everything that would erase it. But the prize is not the antiproton alone. The prize is antihydrogen, the simplest antimatter atom there is, an antiproton with a single positron circling it, the perfect mirror of ordinary hydrogen. And antihydrogen is neutral. It has no overall charge for a field to grip. So the older trapping trick fails, and physicists need something subtler still. They use what is called a Penning-Malmberg trap, which shapes strong magnetic field gradients to catch the faint magnetism of a neutral atom and hold it in a shallow magnetic dimple. It is like trying to balance a marble in the bottom of a bowl made of nothing but forces, when the marble itself would explode the instant it rolled over the rim. The experiment that mastered this is called alpha. On its best runs, alpha can build up to 3,000 atoms of antihydrogen an hour. 3,000 atoms. You could not see them, could not weigh them, could not feel the faintest trace of them on your skin. And yet holding even that many, apart from all matter, is one of the most delicate feats in all of science. Alpha has managed to keep trapped antihydrogen suspended for as long as 100 hours. That is more than 4 full days. 4 days of holding a substance that would annihilate on contact with a single atom of the container, kept alive inside a cage of pure magnetism, touching nothing the entire time. Sit with the smallness of it for a moment. Let the numbers move slowly past you. Even if that factory ran perfectly, continuously, all year long, without a single pause, it would produce only about 30 million atoms of antihydrogen in a whole year. 30 million atoms weigh, when you add them up, around 3 times 10 to the minus 20 kilograms. That is a decimal point followed by 19 zeros and then a 3. It is a mass so far below anything your senses could register that the word tiny does not begin to reach it. You breathe more atoms than that in a fraction of a single breath. A full year of the most advanced antimatter machine ever built yields a quantity that is, for every human purpose, undetectable. Push it up to the level people usually mean when they picture antimatter, up to grams, and the picture turns almost comic. CERN, across all its work, produces something like 10 nanograms of antimatter a year, 10 billionths of a single gram. At that rate, if you wanted to gather 1 full gram, a pinch you could balance on a fingertip. You would have to run the machines for roughly 100 billion years. The universe itself is only about 13.8 billion years old. So making 1 gram of antimatter at the speed we can manage now would take about 7 times the entire age of the universe. 7 universes laid end to end in time just to fill your palm. And that is why antimatter is, without any close rival, the most expensive substance human beings have ever made. The commonly cited figure is around $62.5 trillion per gram, not billion, trillion. To feel that number, hold it against the previous record holder, a medical isotope called actinium-220, which runs about $29 billion per gram. Actinium is already one of the priciest materials on Earth, and antimatter costs more than 2,000 times as much. There is nothing else in the same conversation. Every gram of gold, every flawless diamond, every rare drug in every vault on the planet is essentially free by comparison. You are looking at the single costliest thing our species has ever coaxed into existence, and we cannot even accumulate a speck of it. So why bother? Why pour that much effort and money into a substance you can never gather? Because holding antihydrogen still, even for a few hours, lets you finally ask it questions. And one of the oldest questions was almost embarrassingly simple. Which way does antimatter fall? For decades this was genuinely unknown. Antimatter mirrors ordinary matter in charge, so a fair person might wonder whether it also mirrors the pull of gravity, whether a drop of antihydrogen might fall up instead of down. Science fiction loved the idea. Anti-gravity, reversed physics, a substance that breaks the rules the rest of us live under. There was no experiment clean enough to settle it, because you cannot drop something you cannot hold. In 2023, the Alpha team finally did it. They built a version of their trap standing tall, called Alpha G, held their precious antihydrogen in the magnetic cage, and then slowly, carefully, weakened the fields at the top and the bottom, and watched which way the atoms tried to escape. If antimatter fell up, more would slip out the top. If it fell down, like everything else, more would drain out the bottom. The atoms drained downward. They fell. The measured acceleration came out to about 0.75 g, close to normal gravity within the roughly 20% precision the experiment could reach, and every bit consistent with antimatter falling exactly the way an apple falls. Let that quietly close a door. Antimatter is not anti-gravity. It is not a reversed world with its physics turned inside out. It has the same mass as ordinary matter, the same spin, the same response to the pull of the earth. Drop it, and it falls toward the ground like anything else. The only thing truly opposite about it is its charge, and the one violent thing it does is annihilate when the mirror finally meets the glass. Which leaves us in a strange and humbling place. We can make antimatter, we can slow it, trap it, hold it apart from the world for days, drop it and clock its fall, measure it against ordinary matter with staggering precision, and in every single test it behaves like a perfect twin of the matter you're made of, same weight, same fall, same laws, opposite only in that one property that decides what happens when the two of them touch. There is no crack here big enough to explain anything. The antimatter we build in the lab is the well-behaved mirror. It gives us no reason at all for why it should be so rare. And rare is far too gentle a word. Everything we have ever manufactured, every antiproton in every trap, every atom of antihydrogen alpha has ever coaxed into being across all its years of work, would not add up to enough to power a light bulb for more than a flicker. We have spent fortunes and decades and some of the finest minds alive to produce a quantity of antimatter that, gathered all together, you still could not see. That is the ceiling of what human effort can reach. Now lift your eyes from the trap and turn the question outward. Because here is the thing that should keep you turning it over as you drift tonight. If this is the absolute limit of what we can make, a few tens of millions of atoms a year at a cost of trillions, then the early universe was working on a scale that makes our whole civilization's output look like nothing at all. In the first fractions of a second after the Big Bang, antimatter was not rare. It was everywhere, made in unthinkable abundance. matched particle for particle against ordinary matter, filling all of space as an equal partner. Half of creation, by the plainest reading of the equations, should have been built from the very substance we can barely pin down one atom at a time. We strain every resource we have to hold a speck of it for 4 days. The universe once held oceans of it, and then, somehow, let almost all of it slip away. There is antimatter inside a hospital right now, not in a vault, not behind blast doors. It is inside a person, lying still on a padded table, breathing slowly. This is a PET scan, and it runs on the same annihilation that could level a city, scaled down until it is gentle enough to save a life. It begins with a needle. A technician injects a small dose of a radio tracer into a vein. The most common one is fluorine-18, a radioactive form of fluorine bonded into a sugar molecule that behaves almost exactly like ordinary glucose. Your body cannot tell the difference. It carries the tracer wherever it burns energy fastest. That is the whole trick. Cancer cells are hungry. A growing tumour pulls in sugar at a furious rate, far faster than the calm tissue around it. The tracer follows that hunger and pulls where the metabolism runs hot. An active region of the brain does the same. Light up the sugar and you light up the work. Then fluorine-18 begins to fall apart. It is unstable, with a half-life of about 110 minutes, which means every hour and 50 minutes or so, half of what remains has decayed. Each decay does one strange and specific thing. A proton inside the nucleus turns into a neutron, and in that instant it throws off a positron. A positron is antimatter. It is the mirror of the electron, the same tiny mass, the same spin, the opposite charge. It is the exact particle Carl Anderson first photographed curving the wrong way in 1932. And now thousands of them are being born inside a living body. Quietly, without the patient feeling a thing. The positron does not travel far. It races out of the nucleus at high speed, but the body is crowded with electrons and it does not get to run. Within a millimeter or two, usually less, it collides with an electron. For one instant, the two of them sit side by side, matter and antimatter touching, and then they are both gone. The two particles annihilate. Their entire mass converts into energy, following the oldest rule in physics, and that energy leaves as light. 2 gamma photons, each carrying exactly 511,000 electron volts, the precise energy locked inside the mass of an electron. This is the signature. 2 flashes, always the same brightness, born from a single vanished point. Here is the part the whole machine is built around. Those 2 photons do not fly off in random directions. To keep the balance of momentum, they leave back to back in almost exactly opposite directions, a straight 180 degrees apart. One goes one way, the other goes the precise opposite way. 2 sparks flying apart from a single point, like the 2 halves of a snapped thread pulled straight in opposite directions. That straight line is the entire secret of the image. The scanner is a ring of detectors wrapped around the patient. Each 5111 keV photon flies out of the body and strikes the ring. The electronics watch for 2 hits that land at the same instant, within a few billionths of a second of each other. When 2 detectors on opposite sides light up together, the machine knows something annihilated somewhere on the straight line drawn between them. One line does not tell you much. It only says the event happened somewhere along that path. But the tracer is decaying millions of times over. Line after line after line, each one a fresh cord drawn straight through the body, all of them crossing where the tracer is thickest. Stack enough of them, and the crossings pile up. Where many lines meet, the sugar is dense, and the metabolism is high. A computer gathers all those lines and solves backward for the source. It builds a three-dimensional map of where the tracer went. A tumor appears as a bright hot spot. A working patch of the brain glows. A starved patch of heart muscle stays dark. You are looking at a picture drawn entirely by antimatter, one annihilation at a time. There is a clock running under all of it. Because fluorine-18 decays so fast it cannot be shipped far. A hospital doing PET scans usually sits near a cyclotron, a compact accelerator that makes the tracer that same morning. The isotope is brewed, bonded to the sugar, loaded into a syringe, and used within hours, because by the next day most of it has already vanished. The whole procedure is a race against a countdown set by physics itself. Now hold the scale of it in your mind. This is the same reaction as the most violent event known to science. A single gram of antimatter meeting a gram of ordinary matter would release around 9 times 10 to the 13 joules, roughly 21 kilotons of TNT, more than the bomb that fell on Nagasaki. From 2 grams you could close in one hand. Same conversion, mass erased, poured out as pure light. The PET scan is that identical event, dosed down almost past belief, not a gram. A few thousand positrons, each one annihilating alone, each releasing only a whisper of light that your tissue absorbs harmlessly. The gamma photons are energetic enough to punch straight out of the body and reach the ring, which is exactly why they can be measured from outside without cutting anything open. And it happens constantly. Millions of patients every year lie down inside these rings. Every one of them hosts a slow, quiet shower of matter and antimatter, destroying each other, particle by particle. The same reaction physicists chase at CERN for tens of trillions of dollars per gram is unfolding, for the price of a medical scan, inside a chest, a skull, a spine. Think about how ordinary that has become. Antimatter is the most expensive substance humans have ever made, the hardest to hold, the most alien thing in any laboratory. And a version of it is manufactured in a machine down the hall, injected on a schedule, and annihilated inside people who will get up an hour later and drive home. The most exotic reaction in the universe, turned into a Tuesday appointment. Nothing about it feels violent from the inside. The patient feels no heat, no spark, no pull, just the cool of the table and the soft hum of the ring. But at the scale of single particles, a storm of tiny endings is sweeping through the tissue. Each positron finds its electron. Each pair converts to twin flashes. Each flash is caught, timed, and traced back to a line. The gentleness is real, and so is the annihilation. Both are true at once. That is antimatter in its most ordinary human form, not a weapon, not a fuel, but a faint diagnostic flicker, born and destroyed inside you before you ever leave the table, and notice how little of it there ever is. A few thousand positrons, each lasting less than the blink of a thought, each gone the instant it appears. Gather every positron from every scan in the world, running all year long, and you still would not have a speck you could see, or weigh, or hold in your palm. We conjure antimatter in flickers, and it is gone before we can keep even a trace of it. If a speck is all we can build here at unthinkable cost, then the real question is what happened to all the antimatter the universe was supposed to keep? If a speck is all we can build here at unthinkable cost, then the real question is what happened to all the antimatter the universe was supposed to keep. The equations are clear on this. In the first moments after the Big Bang, matter and antimatter should have poured into existence in equal measure, particle for particle, mirror for mirror, and yet when you look up, in every direction, you find only matter. So the search moved outward, off the laboratory bench and into the sky itself. If the missing half of creation is hiding somewhere, then somewhere out there it should leave a mark. That mark would be light, a very specific kind of light. Whenever antimatter touches ordinary matter, both vanish and become gamma rays, the most energetic light there is. Space is not empty. Thin gas drifts between the stars, and thinner gas still drifts between the galaxies. So if a single star were made of antimatter, its surface would forever brush against ordinary gas, and it would glow with a steady gamma-ray halo that nothing else could fake. A whole antimatter galaxy would blaze at its edges. An antimatter cluster would burn along every border it shared with the normal universe. That glow would be unmistakable, and it would never switch off. So astronomers went looking for it. If you take one thing from tonight, let it be how thorough that search became. They scanned the entire observable sky for that telltale gamma-ray glow, the signature of antimatter pressing against matter. They looked close to home, across the solar system. They looked across the disk of the Milky Way. They looked at other galaxies, at clusters of galaxies, and at the vast cosmic filaments that string the universe together like threads in a web, every scale, every distance, and nowhere, at any scale, did that signal appear. That silence is not a small thing. It places some of the tightest limits in all of cosmology. If large amounts of antimatter were hiding out there, bordering ordinary gas anywhere within reach of our telescopes, we would see it burning. We do not. So whatever happened to the antimatter, it did not simply move to another corner of the visible universe. The books do not balance by hiding the missing half across town. Before we go deeper into that silence, one small thing. If these quiet walks through the physics of the universe help you sleep, a like or a subscribe helps more people find them, and the channel lives on Spotify too. That is all. Now settle in, and let the sky keep talking, because the sky is not entirely silent. It just does not say what anyone expected. When you point the right detector upward, you find that antimatter is genuinely raining down on us in small amounts all the time. It arrives inside cosmic rays, the stream of high-energy particles that pours through space and strikes the top of our atmosphere. Most of those particles are ordinary, but a thin thread of them is not. Among the electrons falling from the sky, there are positrons, the antimatter twins of the electron, each carrying a positive charge where an electron carries a negative one. For a long time, that was not a puzzle. Physics expected a few positrons. When a fast cosmic ray proton slams into a wisp of interstellar gas, the collision can spit out particle and antiparticle pairs as debris. Positrons made this way are called secondary particles because they are byproducts of something else, not survivors from the dawn of time, and the standard picture made a firm prediction about them. As you climb to higher and higher energies, the fraction of positrons among all those cosmic ray electrons should fall. It should thin out. Higher energy, fewer positrons. That was the rule. Then the detectors got good enough to test it, and the rule broke. A satellite called Pamela, launched in 2006, began measuring the positron fraction with real precision. Instead of falling at high energy, the fraction started to climb. Above roughly 10 billion electron volts of energy, a unit physicists write as 10 GeV, the share of positrons went up, not down. That was backward. That was the opposite of what the model said should happen. One instrument can make a mistake. So others looked. The Fermi Large Area Telescope, an orbiting gamma-ray observatory, weighed in and saw the same rise. And then came the most sensitive check of all. In 2011, astronauts installed a device called the Alpha Magnetic Spectrometer, AMS-02, on the outside of the International Space Station. It is a particle physics detector bolted to a spacecraft, sorting the charges and energies of cosmic rays as they arrive. AMS-02 measured the positron fraction with more care than anything before it, and it confirmed the climb in fine detail. The rise above about 10 GeV is real. It is not a glitch in one machine. It is a genuine, statistically confirmed anomaly in the sky. So sit with that for a moment. Something out in space is making more high-energy antimatter than the standard model of cosmic rays can account for. The positrons are there. They are counted. They arrive with more energy and in greater proportion than secondary production alone should allow. The question is not whether the excess exists. The question is what is making it. There are two leading answers, and they could hardly be more different in what they would mean. The first is almost reassuringly ordinary, at least by the standards of extreme physics. Nearby pulsars. A pulsar is a neutron star, the collapsed core of a dead massive star, packed so densely that a spoonful would weigh as much as a mountain, and spinning fast, sometimes hundreds of times a second. A spinning neutron star drags a ferocious magnetic field around with it, and in the storm of energy near its surface, that field can create and fling out positrons at tremendous speed. If a pulsar or two sits close enough in our galactic neighbourhood, it could seed the local sky with exactly the kind of high-energy positrons we see. Pulsars are a strong candidate. They are real objects. We know they make antimatter, and the numbers can be made to fit. But they have not been confirmed as the whole story, and that leaves the door open for the second answer, which is the one that makes physicists lower their voices: dark matter. The unseen material that outweighs everything visible in the universe by roughly 5 to 1, holding galaxies together with its gravity while giving off no light at all. In many theories, dark matter particles can meet their own kind and annihilate, and when they do, they might throw off ordinary particles as debris, including positrons. If it were happening in the halo of our galaxy, it would salt the cosmic ray stream with exactly this sort of antimatter excess, which means the rise in the positron fraction could, in principle, be the first indirect fingerprint of dark matter ever detected. That possibility is thrilling, and it is also difficult. To make enough positrons this way, dark matter would have to annihilate far more readily than the standard cosmological models predict. The rates do not sit comfortably together. So the dark matter explanation has not been ruled out, but it faces a real obstacle, and it remains hotly debated. Pulsars or dark matter? Dead spinning stars or the invisible scaffolding of the cosmos? After nearly 2 decades of data, no one has settled which it is. It helps to hold the two kinds of sky antimatter apart because they tell different stories. The positrons in the excess are the mystery. But there is also a steadier trickle of heavier antimatter, the antiprotons, the antimatter twins of the proton, showing up in cosmic rays as well. You might hope those were relics, actual survivors from the early universe, They are not. The antiprotons we detect are consistent with being secondary particles too, forged when high-energy cosmic ray protons crash into interstellar gas and shatter out antimatter debris. They fit the collisions. They do not need a primordial source. So the naturally occurring antiprotons are, as far as we can tell, ordinary byproducts, not leftovers from their birth of everything. And that is the shape of the whole cosmic search, laid side by side. On the one hand, the Great Sky Survey for hidden antimatter structures comes back empty. No gamma-ray glow from an antimatter star, an antimatter galaxy, or an antimatter cluster, anywhere, at any scale. The universe is not secretly half antimatter, with the two halves living apart. On the other hand, the fine-grained measurements of individual particles do find an excess, a genuine surplus of high-energy positrons that our best models cannot explain and cannot yet trace to its maker. A few researchers push even further into the quiet corners. They ask whether tiny, isolated pockets of antimatter might survive undetected inside our own galaxy. An anti-star here or there, a stray grain of antimatter drifting in the cosmic ray stream. Targeted searches have combed gamma-ray survey data hunting for anti-star candidates, and they have turned up a small handful of sources no one can fully explain. But none have been confirmed. This remains a fringe possibility, actively debated, closer to a question than an answer. The mainstream view holds. Large-scale antimatter is simply not there to be found. So here is where the search leaves us tonight. Somewhere in deep space, something is producing more antimatter than physics can currently explain. It might be an exotic population of dead, spinning stars, seeding the sky with positrons from their magnetic storms, or it might be the faint, indirect trace of dark matter finally showing its hand. Both explanations reach for the extraordinary, neither as one. The positrons keep arriving, counted one by one on a detector strapped to a station orbiting 250 miles above your head, and the argument over where they come from has run for the better part of 20 years without resolving. And underneath that argument sits the larger silence, the one the whole chapter began with. We went to the sky to ask the biggest question we know how to ask. Where did the antimatter go? If the universe made it in equal measure and kept almost none, then the missing half had to go somewhere, and the sky was the widest place to look. We built the instruments. We scanned every direction the light could reach. We checked the solar system, the galaxy, the clusters, the filaments, the faint edges of the observable universe. We listened for the one glow that could not lie. There was no glow. There was only the thin, strange rain of positrons that raises more questions than it settles, and beyond it, the great quiet where an antimatter cosmos should have burned. The absence is not a gap in the data. The absence is the data. It tells us with more certainty than almost anything else in cosmology that the balance was broken early and broken deep, before any star could form, in a moment we can only reach through equations. The universe did not misplace its antimatter in some distant corner. It kept almost none, and the sky confirms it by staying dark where light should be. That is the strange gift of looking outward. You go hoping to find the missing half, and instead you find how completely it is gone. Every telescope, every survey, every patient season of counting particles points back to the same one-sided universe you already live in, the one built from the thin remainder that annihilation left behind. The mystery does not shrink when you search the heavens. It sharpens. It takes on an exact shape, and the shape is emptiness where a mirror world should be. Something out there is making more antimatter than the equations can comfortably account for, and for almost 20 years no one has agreed on what. The trail starts with a satellite called Pamela, launched in 2006, which counted the particles raining in from deep space and found too many positrons among them. Then Fermilab looked and saw the same thing. Then the Alpha Magnetic Spectrometer bolted to the outside of the International Space Station in 2011, measured it with more precision than anyone before, and the anomaly held. Above roughly 10 billion electron volts of energy, the fraction of positrons in the cosmic ray stream stops falling the way plain physics says it should. Instead, it climbs. That upward curve is real. It is not a glitch, not a miscalibration, not a rounding error. It is a genuine excess of antimatter arriving from somewhere in the galaxy, and the whole field has spent 2 decades arguing about the source. The argument splits cleanly in two. On one side stand the pulsars. A pulsar is the collapsed core of a dead star, a city-sized ball of neutrons spinning hundreds of times a second, wrapped in a magnetic field so violent it can tear electrons and positrons out of the vacuum and fling them across space. There are pulsars close enough, in galactic terms, to seed the local sky with high-energy positrons. The numbers roughly fit. The mechanism is understood. And that is the quieter, more conservative answer, the one that asks the universe to do nothing it has not already been caught doing. On the other side stands something far stranger, dark matter, the invisible mass that outweighs every visible star and cloud of gas by a factor of 5, the stuff whose gravity holds galaxies together while giving off no light of its own. If dark matter particles are their own antiparticles, or if they can meet and annihilate, one of the leftovers of that annihilation could be a shower of positrons. In that reading, the excess is not the exhaust of dead stars. It is the first faint fingerprint of the dark sector, the closest anyone has come to touching the thing that makes up most of the matter in existence. Before you go further, if this quiet unravelling of a real scientific fight is the kind of thing you like to fall asleep to, a like or a subscribe genuinely helps this channel keep making them, and the audio lives on Spotify too. You can feel why the dark matter answer is the one that sets pulses racing. It would be enormous, but wanting it does not make it true, and the honest weighing does not favour it. For dark matter to produce the observed flood of positrons, the particles would have to find each other and annihilate at a rate far higher than the standard cosmological models allow. Those same models describe how galaxies formed, how the early universe cooled, how the cosmic background settled into place, and they leave very little room for dark matter that reacts as eagerly as this signal would require. So the dark matter explanation is not ruled out. It has never been ruled out. But it has to fight uphill against everything else we think we know, and that is why, after all this data, it remains contested rather than confirmed. The pulsar side has its own gap. Pulsars are a strong candidate. They are not a closed case. No one has yet shown that the known pulsars, in their known positions, produce exactly the excess we measure, and nothing is left over. The candidate is credible and incomplete at the same time, and so the field sits in an uncomfortable and honest place, where the boring answer is probably right but unproven, and the thrilling answer is probably wrong but not dead. Nearly 2 decades of the best instruments ever flown, and the most anyone will tell you plainly is that they do not yet know. Underneath that argument runs a second, wilder one. If a little antimatter is loose in the galaxy, could whole objects be made of it? Could there be an anti-star burning somewhere in the Milky Way, built from antimatter atoms, shining light that looks identical to ordinary starlight from a distance? A star like that would betray itself the moment its outer edges met the thin, ordinary gas that drifts between the stars. Antimatter touching matter does not mix. It annihilates, and it annihilates into gamma rays, a specific hard glow at a specific energy. So people went looking. A targeted search sifted the Fermi-Lat gamma ray catalogue for sources that carried the telltale signature of an anti-star, and it came back with a handful of candidates, a small number of points in the sky that could not be immediately explained away. Hold that word lightly. Candidate, not discovery. Every one of those signals can be something else, a distant spinning pulsar, a feeding black hole, a background source misread. None has been confirmed as an antistar, and most physicists treat the whole idea as a fringe possibility rather than a live finding, worth a careful look precisely so it can be ruled out, rather than because anyone expects it to survive. The same skepticism greets the reports of antihelium. A few times, cosmic ray detectors have logged events that look like the nuclei of antihelium atoms drifting in from space, which would be far harder to explain than a stray positron, and much closer to evidence of real antimatter structures out there. Those events remain unverified. They sit in the notebooks, tantalizing and unconfirmed, waiting for either more of the same to make them undeniable, or for the tally to quietly explain them as noise. It is worth being just as honest about the ledger closer to home, because the same caution runs through every number in this field. You will see antimatter described as the most expensive substance ever made, priced at something like tens of trillions of dollars per gram. Treat that as an order of magnitude illustration, not a receipt. The figure swings wildly depending on how you count it, whether you tally the raw energy poured into the accelerators or the full cost of the machines and the people and the decades. The point the number is trying to make is sound. Antimatter is staggeringly, almost incomprehensibly costly to produce. The exact digits are a gesture at that truth, not a precise measurement of it, and anyone who quotes them to the dollar is pretending to a certainty the physics does not have. That is the texture of this whole corner of science, a real excess with no agreed cause. A handful of glowing points that might be antistars and probably are not. A few unverified nuclei that could rewrite the picture or dissolve into background. Prices that are honestly only guesses. Every thread leads outward, into the dark, towards something you can see the shape of but never quite reach. Picture a campfire seen from very far off across open country at night. You can make out the glow. You can tell someone lit it, that something is burning there, that it is warm at the center. But the ground between you and the fire keeps stretching, and no matter how long you walk toward it, the light stays the same distance away, a smudge of orange that never resolves into flames you could warm your hands on. That is the positron excess. That is the anti-star. That is the anti-helium event logged and set aside. a signal that says clearly that something is out there, paired with a distance that refuses to close, and so the debate stays genuinely open, which is the most truthful thing that can be said about it. The pulsars are winning on plausibility and losing on proof. The dark matter is losing on plausibility and refusing to die. The antistars are almost certainly not there, and yet the search goes on because almost is not never. Every direction the instruments turn, they find either ordinary matter or an unexplained hint too faint to build a conclusion on. There is no confirmed pocket of antimatter anywhere. There is no anti-star with a name. There is no galaxy across the void that flares in gamma light, where its edge grinds against ordinary gas. No continuous burn along any border in the sky to mark where a mirror world begins. If a mirror world existed at any real size, it could not stay quiet. It would have to announce itself in that hard gamma glow, constantly, at every seam where its matter met ours. So the searchers keep listening for that announcement, across the solar system, across the galaxy, across the clusters and the great filaments of the cosmic web, and they keep coming back with the same result, the same absence, the same fire that will not let itself be reached. The sky, scanned in every direction and every distance, gives back only silence. The sky, scanned in every direction and every distance, gives back only silence. No hidden mirror world announces itself. No far-off glow betrays a galaxy built the other way around. And so the search for the missing half of creation ends where it began, inside you, in the ordinary matter of your own hands, which turns out to be the strangest evidence of all. Think about what you are, quietly, without rushing. Every atom in your body traces back to a single instant when the universe filled with equal parts matter and antimatter, born together, each the exact mirror of the other, same mass, same spin, opposite in the one property that decides what happens when they touch. By the best equations we have, those two halves should have found each other completely. They should have annihilated pair by pair until nothing was left but a bath of light, spreading forever through an empty cosmos, with no one inside it to notice. That is not what happened. For every billion antimatter particles there were 1,000,000,001 particles of matter, one extra, out of 1,000,000,000. When the great annihilation swept through the first cooling instant of the universe, nearly all of it cancelled into gamma rays, more than 99.9999% of everything gone in a flash. And the tiny remainder, that one leftover part in 1,000,000,000, is the entire physical world. It is every star you have ever seen. It is every planet, every ocean, every grain of sand. It is the neurons drifting now towards sleep. You are the survivor of a near-total erasure, the residue the fire forgot to take. Sit with the smallness of that number. 1 in 1,000,000,000 is the margin by which anything exists at all. Shift it even slightly. Make the two halves perfectly even, and the story of the cosmos ends in its first second, silent and bright and empty. You are here because the balance was broken just barely, in a way our physics still cannot fully explain. And that is the quiet strangeness this whole night has been holding. We know the imbalance is real, because we are made of its leftovers. We have even caught the universe treating matter and antimatter differently, in the decay of kaons long ago, and now at last in the baryons themselves, the very particles that build protons and neutrons, measured to odds of about 1 in 10 million that it was a fluke. Nature does play favourites. The mirror is not perfect. We have proof. But every time we measure how strongly nature cheats, the answer comes back the same. It is far too small. The known asymmetry, the whole catalogue of differences we have ever confirmed, falls short by many orders of magnitude of what it would take to leave behind a universe this full. The crack in the symmetry is real, and it is nowhere near wide enough. Something else tipped the scales. Something we have not found. Some particle or force or mechanism still hidden beyond the edge of what we can measure. That missing piece is one of the largest open questions in all of physics, and it is the one that quietly holds this entire picture together. So here is the paradox the title promised, and here is where it lands. Antimatter is not science fiction. It is not reversed gravity or an evil twin of physics. It is matter's exact reflection, and when the two meet, they vanish into pure energy. The same annihilation that lights up a hospital scan and, scaled up, would outshine a nuclear weapon. The universe began with equal parts of both. By its own laws, those parts should have destroyed each other down to nothing. A cosmos that, by its own equations, has no right to exist. And yet it does. And yet it holds you. The chair beneath you, the warmth of your own body, the slow rhythm of your breathing, all of it is the ghost of an annihilation that almost took everything. You are what the light left behind. There is a strange comfort in that, if you let it settle. The bomb that should have gone off completely did not. The subtraction that should have reached zero stopped one step short, and in that single spared step, the whole of existence unfolded, galaxies and rivers and the quiet dark of a room at the end of a long day. You do not need to solve the missing mechanism tonight. The physicists will keep chasing it, in beams fired 800 miles through solid rock, in clouds of antihydrogen held in magnetic bottles, touching nothing. The question will still be there in the morning, patient, unhurried, the way the best questions are. For now, let it simply be true. You are the residue of a nearly total fire. You are the one part in a billion that the annihilation forgot. Every equation says you should have been erased into light before the first second was over, and instead you are here, warm and whole and drifting, held up by a broken symmetry no one has yet fully explained. Let your thoughts slow now, the way the early universe slowed as it cooled. The frantic collisions fading, the light spreading out, everything settling into the calm that came after. There is nothing left to hold on to. The imbalance already did its work, long before you were born, long before the first star. All that remains for you is to rest inside the world it left behind. You are the leftover. You are the surviving trace. And the universe that should not exist has kept you anyway, gently through every night there has ever been. Sleep well tonight. Good night.